In this video, I want to discuss another part of sensitivity analysis that is related to changes in lower bounds or upper bounds of decision variables. So if you recall in the earlier video segments, several lectures, I showed you the impact of changes in the objective coefficients, like 350, 300 here. Then there were several segments of videos that talked about changes in the right-hand side values of constraints. And this one is about lower bounds and upper bounds. In this example, we don't have upper bounds on decision variables. And we will be using here something called reduced costs, which you can find in sensitivity reports of Excel or Gurobi. So unfortunately, this problem that I considered before with two decision variables, a product mix problem, is not very interesting for as an example problem, because both variables have only lower bounds and they have no upper bounds. And the secondary thing is that both reduced costs are zero when you look at the sensitivity report, this one or this one. So I want to introduce a slightly modified problem. So this modified problem is still the product mix problem of Blue Ridge Company, but now there is a third product here, Typhoon Lagoon. So there is data provided for it. The same resources as before, and the same first two products are there. And one more thing is that the profit per Hydrolux, which was originally 300, changed to 400. But there is also another thing that we now have a maximum number of units that we can produce for any product. Before there was no limit, but now there is a limit. So if you see the modified model, right, there is now 3 decision variables defined just in one line. And this is the changed profit. It was 300 before, now it's 400. And then there is the third variable for which appears in the objective and all the constraints. And the important change also, in addition to lower limit 0, every variable has an upper limit, also 150. So if you solve this problem in Excel or in Gurobi, for example, through Python interface, then you get an optimal solution, x1, x2, x3. The stars indicate optimal values of decision variables, 0, 50, and 150. So what I want you to notice first is that the first variable is actually equal to the lowest possible value, lower bound. The second variable is somewhere in between. And the third variable is 150, is on the upper bound, right? And then the optimal objective function value, if you plug in these values into this objective, we get $83,000 of profit, right? So this is the profit maximization problem, and the maximum profit we can get is shown here. So if you solve this problem and you get the optimal solution, of course, we can obtain also sensitivity information, either from Excel or from Gurobi, right? Here is the sensitivity information, and this is, of course, the same problem that I showed you, the same model that I showed you just a moment ago. And you see in Excel, unfortunately, the sensitivity information in terms of changes to the upper bounds and lower bounds of decision variables is limited. It's only provided, what we are provided only is reduced cost. We are only provided with reduced costs. However, in Gurobi, you can also get a certain range for lower bound and certain range for upper bound in which the reduced cost can be applied. So the main thing I want you to get from this is that reduced cost for lower bound or for upper bound of the decision variable works in the same way as shadow price for the right-hand side. So when before we had a shadow price that told us marginal value of extra pump. Here we have reduced cost that says marginal value of changing either a lower bound or an upper bound, right? So again, note that the unit of reduced cost is like the unit of shadow price. We have to take how much benefit in terms of the objective, which is now dollars, right? Dollars of profit. Will the change in the bound give you, right? Per unit of the change in the bound will be given, right? So in this case, for example, the units of all reduced costs will be dollars per unit of product, right? Every lower bound is saying minimum 0 units of Aquaspas or Hydrolux or Typhoon Lagoons and maximum 150 Aquaspas and so on, right? So reduced cost is like shadow price, and these ranges are actually also ranges of feasibility, but they are both, one is defined for lower bound, and the other is defined for the upper bound. Right, so we have two range of feasibilities, right? And this is the range, again, as before, the ranges of feasibility were in which shadow prices work for right-hand sides. Now the range of feasibility is the range in which the reduced cost will work as a marginal value of increasing lower bound or upper bound, right? So important thing to understand is that reduced cost for now, which bound will the reduced cost work for? Well, it depends on which bound is the binding bound. So if lower bound is binding, then reduced cost is the marginal value of increasing the lower bound. And then the marginal value of increasing the upper bound is going to be 0. And when I say increasing, I mean, for an increase of lower bound, there is an increase in the objective function. For a decrease of lower bound will be the decrease, the negative increase, right? So then a decrease of the objective function value, right? So for example, when we look at this, the optimal solution, as you see it here also, 0. For the first decision variable, the optimal value is 0, right? We see it also here, right? So why is 0? Probably because the solver was trying to decrease it as much as possible. The reduced cost then will indicate how much increasing the lower bound will change the objective. But then we can change the upper bound without impacting the solution or the optimal objective function value. If the upper bound is binding, then reduced cost is the marginal value of the upper bound. So in this example, the upper bound is binding for the third variable. The solver chose an optimal value of the third variable, 150. 150 Typhoon lagoons should be produced, right? And this happens to be the maximum value, and then this reduced cost then applies to the upper bound. So it tells us if we change this upper bound 150 for variable number 3, x3, then the reduced cost will tell us what will happen to the optimal objective function value. And then if neither lower bound nor upper bound is binding, then reduced cost will actually be 0, and you see this here. This is 50, the variable is 50. It's not equal to lower bound 0, not equal to upper bound 150, right? The lower bound is also here, and the upper bound is also here. It's neither equal to 0 nor to 150, so it's somewhere in between. The reduced cost is always 0 in this case, and basically it actually works for both of those bounds. Changing the lower bound or changing the upper bound within the range of feasibility for each of them will not change the optimal objective function value. Actually, it will not even change the optimal solution. And one more thing that I will not focus in this video much on is that you can actually have an extended 100% rule. Like we had a rule for right-hand side changes. If you change more than one coefficient, then you can still use shadow prices provided that the percentage change, the total percentage change of right-hand sides does not exceed 100% of allowable changes. You can extend it actually to lower bounds and upper bounds. So you could say if there is a change in the right-hand side and maybe in one lower bound or in an upper bound, or right, a combination of those, as long as the relative change, percentage change of all, total percentage change of all those values does not exceed 100%, you can use shadow prices and reduced cost to determine the change in the optimal objective function value. Anyway, so let me move to a couple of examples. So the first example is, what if upper bound for x1, increases by 10? So first thing to notice is that x1 actually is equal to 0, right? Optimal solution, x1 and optimal solution is 0. So it is not equal to the upper bound, and we're changing upper bound. The upper bound is 150 for the first variable. So we're changing now an upper bound, but this is not a binding constraint. Therefore, what can we say? We can say that given that lower bound 0 is binding for x1, and upper bound, which is now 150, is not, right? The optimal value of x1 is equal to optimal value is equal to 0, right? So the reduced cost, that is, what is the reduced cost? Reduced cost is minus 50, minus 50. And let me actually put the unit here, dollars per aqua spa. Why per aqua spa? Because product 1 is aqua spas, right? Number of aqua spas. So this minus 50 actually is the marginal value of increasing lower bound, is the marginal value of increasing the lower bound, right? Lower bound. And the marginal value for of increasing upper bound is actually 0 in that case, $0 per aqua spa, right? So now, remember, we are now increasing the upper bound. So this is the bound, the marginal value we should be using, right? Should be using this marginal value to determine the change in the optimal objective function value. So in that case, if we take upper bound, first we have to also see what is this increase, right? This increase by 10 will change the upper bound to, right, 150 plus 10 is 160. And we have to ask ourselves, is this within the range of feasibility for the upper bound for variable x1, right? So upper bound was 150. This is the range of feasibility. And it happens to be a range. It is within the range of feasibility for upper bound, which is from 0 to plus infinity, right? So this range, so the change in the optimal objective function value, let me copy it from here, can be calculated exactly using the marginal value that is equal to 0, right? So the optimal objective function value will increase by 10, right? This 10, the increase, this 10 that I increased the upper bound times the marginal value. But since the marginal value is 0, that will be 10 times 0, so it will increase by 0, right? So actually it will not change, i.e. it will not change, right? And also, old optimal solution will still be feasible, and we relaxed a non-binding constraint. So the old optimal solution will still be optimal, right? So there's no change in the optimal objective function value and no change in the optimal solution in this case. And notice this is the same case where, like, we were changing the right-hand side of one of the constraints that was non-binding. When we were relaxing it, again, the solution wasn't changing and the shadow price was 0. The optimal objective function value was not changing either. Another example, what if lower bound for x1 increases by 20? So first we were increasing upper bound for x1, and we said marginal value was 0 because the bounding bound was lower bound, right? It was the lower bound of 0. So now we're increasing the lower bound. So obviously, right, we have to say the lower bound, which is equal to 0, is binding for x1, right? It is binding now, right? We can say the optimal value of x1 equals 0, right? So obviously, in this case, the reduced cost, which is equal to minus $50 per aqua spa, is the marginal value of the lower bound of increasing, right? Lower bound. So this is where the reduced cost can be applied, right? And now we want to see, is this change, the increase, right? It was 0 plus, we increased it by 20. It is 20. It is within the range of feasibility, right? Why do I see it? Range of feasibility for this variable, now for the lower bound, right? So range of feasibility for LB, right? This range of feasibility is minus 32.5 to 22, right? So it is below 22. Actually, we were getting close. We are at 20, right? So, right? So the change in the optimal objective function value can be calculated exactly using reduced cost equals minus 50, right? This reduced cost minus $50 per aqua spa, right? So, so if we can be, so what is the new value, right? The optimal objective function value will increase by what? By an increase in 20 causes an increase in the optimal objective function value by the same 20 times this marginal value, which is now the reduced cost. So it will be an increase of 20 times minus 50. Now, bear with me. I'm saying an increase by minus 1,000, right? But how do we interpret increase by minus 1,000? Actually, it will decrease by 1,000, right? In adding minus 1,000 will mean subtracting, so it will be 83,000 here. It will be 82,000, right? Dollars, right? So now what else can we say about the optimal solution? Now we know the objective function value. We will lose if we force this production of the product that was actually not profitable. Why did the solver set the optimal value to 0? Well, the other options were more profitable relatively, right? Using the resources for more profit. So now forcing 20 units causes a loss. For every unit, we lost $50. So in total, we lost 1,000 of relative profits, right? What can we say? Well, given that we restricted a binding constraint, right? The old optimal solution is no longer feasible, right? I mean, if we change the lower bound from 0 to 20, that means there is a constraint x1 greater than or equal 20. Just for x1, the other lower limits remain 0. But optimal value of x1 is 0. So it's no longer feasible, right? So it is also, right, no longer optimal, right? The optimal solution will change then, right? And also we could have said, if not for this reason, we could have said that given that the optimal objective function value changed, the optimal solution must be changing too, right? How do I know this? I mean, because, right, this optimal objective function value, we didn't change the coefficients, 350, 400, 420, right? So if we plug in the same optimal solution, we will get 83,000, but we just said we should get 82,000. So it must be achieved by some changes in at least one decision variable, right? At least one decision variable will change its value. Therefore, we know the optimal solution must be changing too. Another example is what if lower bound, again for x1, increases by 30. So before we considered lower bound increased by 20, but now we increase it by 30, right? So the same thing applies as before. Lower bound is 0. It is a binding constraint for x1, right? Optimal value of x1 is 0. So this reduced cost that we see here, minus 50, applies to this the marginal value of increasing the lower bound, right? However, if you now can calculate the increase, right, add the increase, right, so it's 0 plus the increase of 30, it is 30, right? This is not within the range of feasibility for the lower bound. The range of feasibility is up to 22, right? So this is not within the range of feasibility of lower bound, right, or for lower bound, which is from minus 32.5 to 22, right? So this time, the change in the optimal objective function value cannot be determined using the reduced cost exactly, right? So this is before we could determine exactly how much the profit will change. Now we just can say something that it will change, but we cannot determine exactly by how much it will change, right? So for this is not within the range of feasibility, we cannot calculate the change. However, what we can say is that if we first increase LB lower bound to 22, right? Just to 22, to the upper limit of the range of feasibility, right? Then the reduced cost should work, right? So the optimal objective function value will increase by 22 times reduced cost, which will be, right, 22 times minus 50, which is minus 1,100, right? So, i.e., it will decrease by 1,100, right? Now, a further increase in this lower bound is a further restriction, right? Is further restriction of the model, right? How do I know this, right? Because if I'm increasing a lower limit, I'm reducing the size of the feasible region. I'm removing some feasible solutions, they become infeasible, right? So if this is a restriction, right, so it can only worsen the objective function value, right? So because it makes the problem harder, you know, if there are fewer choices, we can only get worse, right? It might not get worse, but it will definitely not get better, right? So it might only decrease, right? The worsening is decrease the optimal objective function value further, right, or more. So in that case, the 83,000 minus this 1,100 dollars, right, that we calculated here, the decrease, this is an upper bound on the optimal objective function value, right? So I know it will decrease by this, but it might decrease by more than this. So let's actually calculate. So this is going to be 81,900, right? This is an upper bound, right? So we cannot calculate exactly the change in the optimal objective function value, but we can find an upper bound. Another way of looking at it is that given that we are restricting the model, right, with this increase of the lower bound, we are restricting the model from 0 to 30, right? We know up to 22 reduced cost is this minus 50. But what will be the reduced cost above 22, right? Well, for every additional unit of this lower bound, right, this demand, this increase in the minimum requirement of product 1, the reduced cost, first it's minus 50, then it cannot get better, it can only get worse, right? So when we increase LB above 22, the reduced cost must be minus 50 or worse, right? So worse, so that means even less than minus 50. And by less than minus 50, I mean minus 60, minus 70, minus 100, I don't know, right? So in that case, if I just assume 50, this is going to be like the best case, right? The decrease of the profit by 50 will be like the best case I should expect. So in other words, 83,000 minus, plus, right? We increase by 30. So I add here 30 times reduced cost, right? But that's actually 30 times minus 50, right? So this is minus 1,500, right? Which will be 81,500, right? This value is actually an upper bound on the optimal objective function value, right? Why do I claim this? Again, because minus 50 is the reduced cost for the first 22 units, right, of increase in the lower bound. But beyond that value, things can only get worse. As you restrict, the costs or the decrease in profit must be at least 50, maybe even more. So by this principle, again, I come up with the best possible value I might be achieving is this, maybe it's even worse. So, right, so overall, if you put those two together, obviously, this is a stronger upper bound, so we should expect at most 81,500, right? And again, as before with right-hand sides, when we were changing them, when we were beyond the range of feasibility, we could determine at least an upper bound, and now we also can determine at least an upper bound on the optimal objective function value. What about the solution, right? So putting the above two facts together, the upper, the right 81,500 is the upper bound or an upper bound on the optimal objective function value. And what about the solution? Well, again, as before, either, right, given that we restricted the a binding constraint, or given that optimal objective function value changes, right? Both of those facts actually force the solution. The fact that they mean the solution must be changing. So the optimal solution must change too. Another question, what if lower bound for the third variable increases by 100? So we need to notice that for the third variable, lower bound 0 is not binding, right? Lower bound for the third variable is 0, right? And it is not binding for the variable x3, right? The upper bound is binding, right? So upper bound is binding, right? The optimal value of x3 equals 150, right? As you can see here, x3 is equal to 150. So in that case, reduced cost that is equal to 20, you see it here for the third variable, right? 20 what? Dollars per Typhoon Lagoon, right? Which is the third product. This reduced cost is the marginal value of increasing the upper bound, right? But not lower bound, right? So the marginal value for increasing lower bound is 0, right? Or $0 per Typhoon Lagoon, right? So now we need to see the lower bound plus the increase, right? It's 0 plus 100, which is 100. Is it within the allowable, range of feasibility? What's the range of feasibility for the lower bound? It's actually from minus infinity, right? That's negative, very large in absolute terms, negative value, right? That's indicating minus infinity up to 150. So this 100 is below 150. It's not exceeding 100. So it is within the range of feasibility for lower bound, right? Which is from minus infinity to 150, right? So the change in the optimal objective function value can be calculated exactly using the shadow price, reduced cost. And not reduced cost, right? Reduced cost is for the upper bound, so using marginal value 0, right? 0 Typhoon Lambda, this one, right? So what's the optimal objective function value will then increase, right? And again, for an increase by 100, we have an increase by 100 times this marginal value, which is 100 times 20, right? Sorry, 1 times 0, which is equal to 0. So it will still be 83,000, right? And given that we restricted a non-binding constraint, right? This lower bound, 0 for the third variable was not binding, right? The optimal value was 150. We restricted it, but we did not restrict it so much that the optimal solution would stop being feasible. It is still, this solution is still feasible. We want the third variable to be at least 100, but it is 150, right? So we can say, but the old optimal solution is still feasible, right? So it will still be optimal, right? So this is again, you see by analogy, when we were changing the upper bound for x1, it was not binding and the reduced cost was not applying to it. The marginal value of changing it was 0. Now we're changing the lower bound, and again, this is not binding, right? The upper bound here is binding. And so for the lower bound, the reduced cost doesn't apply. The reduced cost is not the marginal value for lower bound. The marginal value here is 0 for the non-binding bound, right? Okay, last example. What if we change lower bound or upper bound for x2? So I made it a little bit more generic example, right? So for x2, x2 is equal to 50. So it is neither equal to 0 nor to 150. It's neither lower bound nor upper bound that's binding, right? So we can say neither LB nor UB is binding for x2, right? Right? We can say x2 star is equal to 50. The optimal solution is 50, right? So marginal values for increasing either bound, right, is 0, right? 0. In this case, it's $0 per hydrolux because the second variable is number of hydrolux stops, right? So as long as LB remains within its range of feasibility, what is the range of feasibility for lower bound? It's from minus infinity to 50, right? So from minus infinity to 50. And by analogy, and as long as UB remains within its range of feasibility, right, which is now here 50 to plus infinity, 50 to plus infinity, right? What will happen? The optimal objective function value will not change. We know this because reduced cost is 0. So whatever increase, decrease here, increase, decrease here, right? Lower bound or upper bound within this range, right? The impact will be 0 on the optimal objective function value. And also we will be changing the bounds of non-binding constraints, but without changing, exceeding 50 for lower bound or going below 50 for the upper bound. So the optimal solution that we have here will still be feasible, right? So we can say the optimal solution will, so we can stay with the optimal objective function value will not change, and the optimal solution will still be feasible. So it will still be optimal, right? However, if lower bound, or by analogy, upper bound, is not within its range of feasibility, right? So let's say if the lower bound is increased above 50, right? Like let's say to 60, then this is no longer feasible, right? So the optimal solution will no longer be feasible. So it will no longer be optimal either, right? Right, so the optimal solution will change, and also the optimal objective function value will be 83,000 or less, most likely less, right? But very likely it will drop because we just made the optimal solution infeasible, and when we restrict the model like this, we should expect a decrease. Only if there were multiple optimal solutions to start with, we could still get $83,000 with another optimal solution. And of course, you see, so the examples I showed you here, the 5 examples, we considered changes of a single objective, not a single lower bound or upper bound, right? This is, remember, they were happened all to be equal. Lower bounds, all of them 0, upper bounds 150, but they could be different values. And I considered changing one coefficient at a time. I could also show you examples of the 100% rule. So we could, for example, change one lower bound and change also another upper bound. And as long as the percentage of changes is within 100%, measured as relative to allowable changes, we could say we could apply the reduced cost to determine the change in the optimal objective function value. And also we could extend this by another thing, right? So we could, for example, say, what if the number of pumps here increases by something and one lower bound decreases or another upper bound increases? Again, as long as these changes measured as percentage of allowable increase or allowable decrease, right, do not exceed 100% in total, we can apply, right, for the change in the right-hand side. We use the shadow price. For the change in lower or upper bound, so we use reduced cost or a marginal value that applies to it, and we can still determine what's the change in the optimal objective function value. And of course, if the optimal objective function value changes, the solution will also be changing. So this is the third part of sensitivity analysis, right, related to lower and upper bounds. And as I said, the most important thing to remember is that changes in the lower bound and upper bound, we have impact on the optimal objective function value through reduced cost, in the same way as changes in the right-hand side impacted the optimal objective function value through the shadow price values, right, which we had for each constraint 1.